Guten Morgen. Hatten wir noch einen Platz heute Abend? Wir haben 8. Also, du hattest Max gesagt.
Also, genau, ich wollte dem Max noch zusagen, weil ich nur gesagt habe, okay, das macht das sage ich uns.
And that's at the max. All right, good morning, everybody. Let's get started. This is the proposed space RG, systems and protocol aspects for circumstellar environments and beyond. And yeah, we are an IETF research group. Nevertheless, it sounded good for me. For me, okay. I'm closer to the mic now. So we are an IETF research group, a proposed one. Nevertheless, we are part of the IETF, so our note well applies. And just to remind you, many of you have probably seen this before, but it's important. So we are a professional organization, and we do value professional interactions, courtesy towards others, and avoiding any kind of harassment of any sort. In case any such should up, you're welcome to talk to the ombuds team, and in order to have that taken care of. We also advise that whenever we are making IETF contributions, this is covered by certain regulations, and if you are aware of any IPR that is being that applies to technologies being discussed here, you ought to be disclosing that. Details all to be found there. Finally, briefly to note that we are recorded in audio and video, so whatever you say is you may appear on camera. And if any questions, please talk to the area directors. I'll give you a second to digest that slide, maybe look at the QR code and go through the details in case we have people who are just following today. Okay, so we are we are in the IETF, so we are an organization that meets at the same time at the IETF, but we are not doing standards, we are conducting research. I know there's lots of confusion about different types of RFCs. We may produce documents at some point, they may turn out to be documents outside the IETF, they may turn out to be documents that are informational or experimental RFCs of some sort, but we don't do standards, just to make sure that this is clear, that we have a clear delineation from the rest of the IETF processes. We may, though, provide and have findings and share insights that might influence other groups in taking smart decisions about how they want to go about their standards development. And yeah, this is our first meeting. So Juan Freire and myself, Jörg Ott, we are chairing this research group. We get generous support from Nishant Santri in the back office, kind of. He is also happily agreed to volunteer and take notes for the day. And so welcome to our first official meeting. Our agenda today has 5 talks. We'll come back to that in a moment, just to give you an introduction over this and double check if there's any agenda bashing desired. If not, then I would effectively proceed on. All the materials are, of course, already in the data tracker available. So first 3 talks are going to be on site. The last 2 ones are remote, but we'll come to them in a moment. Quick background about the emergence of the space RG. The idea came about around IETF 120 in Vancouver when some folks got together and discussed this. We had 2 side meetings, then in Bangkok and in Madrid, with a bunch of different presentations covering a very broad area of interest of topics, starting from looking at measurements, looking at modeling aspects for satellite and deep space systems, discussions on sustainability, in this specific case that we discussed there of LEO constellations, looking at routing mechanisms, but also looking at computing in space. So this is just a very short summary sample of the breadth that we have been looking at, the stuff that people put forward as could be interesting here. During all these meetings, we also spent quite some time on charter bashing, collecting community feedback to get an idea on what we should be doing and what we shouldn't be doing, which turned out to be a pretty hard thing to find out in the end. I'll come to that in a moment when we talk about our future steps or next steps starting today. We have a bunch of resources. We have the official IETF page. We have a GitHub repo where we have some background material as well, where we're going to collect documents and other things. There's also a history of the talks and slides from the side meetings available. And of course, we have a mailing list, space@ietf.org. What are we trying to do? So we are a research group. That's what I mentioned already. So we are not going to do standards, but we may do other documents, and that may also involve internet drafts. The first individual internet draft submission was already made under our name. And so in general, we are looking at networked nodes with high mobility and topology dynamics as we find them in space. And they may face environmental and resource constraints of different natures. We may have other externalities to be taken into account. We may want to look at sustainability aspects. So there's a broad range of things that we could be doing. We don't want to become this is my latest Starlink measurement paper group. I know that there's roughly probably 100 publications on Starlink performance in different flavors every year now. And we clearly want to have a broader scope and not just recount measurements that were done specifically on that. Of course, there are valuable measurements from all kinds of perspectives, but we should be taking into account that we want to be broad and inclusive towards other research, and we'll also prioritize our agenda time to be broad rather than too specific. Even though we do have a Starlink talk today, but that's a cool one. So this is they are allowed. So what we want to do is learn about cool research ideas and findings, share ideas, methodologies, software, and data. So as always, we worry about reproducibility of research, comparability of research, so anything that can help us as a community to come up with best practices of some sort, simulation or evaluation setups, infrastructure, parameters, tools, so anything that is useful for researchers to share, to come to a common understanding on how different systems compare to each other. This is all very much welcome and definitely in scope for here. Besides that, we certainly want to talk to each other to build a community, but also reach out to those who are not yet here. So if you have people in your professional contact circles who would be of interest to this, reach out to them so that we can get as broad as a perspective as possible. What we don't want to do is, as I said this before, we don't want to do protocol specs because we are a research group. We have other groups in the IETF that do specifications. We have the delay tolerant networking working group. We have the time variant routing working group, taking IP to other planets, TCPM, QUIC, MOC, and you can probably name a few more that would be relevant here. We may have findings to share that could inform the processes and the designs that are done in these groups, but we won't be doing any direct work competing with them. This is a clear mandate for us to stay out of somebody else's turf. Well, now, so we want to be a forum that brings together people from different communities, ideally cross disciplines. And as I said, we are trying to be open. We want to listen and understand different perspectives. So our charter has intentionally a relatively broad scope in terms of technologies and fields. And since we are still a proposed research group, one of our tasks for the next 12 months is roughly to understand where we are going. And this is going to be a joint effort driven by also you as contributors. So we want to build an open exploratory community that is reaching out to others. And as I said, we have a broad scope and we need to understand over time what people's interests are, where we want to focus on maybe some first pieces of work we are going to do. So in the end, your contributions matter. And because your contributions matter, I think we should be shutting up now and invite our first agenda presenter, who is Jason Girard. Dirk.
Yeah, just quickly, Dirk Kutscher. So I just wanted to say I'm really happy that this came together, and thank Jörg and Tuan for driving this. So, so what you said on the previous slides, I think this was very good. So I'd like this group to be driving the systems research in this space environment that you described. And so for that, it's okay to start with a relatively, broad agenda and invite different topics. But so that's a call to the community, right? So this group really needs contributions, active contributions from the community to be successful in order to help the chairs to shape the group's agenda and charter. And I hope we can kind of lift this off. And thanks again for driving this.
Oh, thanks. Okay, then we could start with Jason. I'll bring up your slides. Here's a clicker. There's a microphone.
Thank you.
And do stick around this area so the camera captures you.
Gotcha. Camera's right there?
Yeah.
Perfect. All right. Hello, everyone. My name is Jason. Today, I'm going to be giving a talk on optical link scheduling. Little bit of background about me. So most of my experience is in physical layer and embedded systems. So I'm software engineer at Amazon, working at Amazon Kuiper on the OSLs, the optical intersatellite links. And I'm also a PhD candidate at Concordia University here in Montreal, working on interplanetary networking and specifically on the scheduling of free space lasers. So before we get into the talk, I just want to make a disclaimer, and I want to make it very clear. So all the opinions and everything that I'm talking about today is my own opinions, my own ideas. Any plots, figures, data is from my own research or from things that I'm citing in the presentation, and this is not an actual talk for Amazon or for Kuiper, and it doesn't represent anything that's non-public. So because this is a general space networking group, and I'm going to be talking about optical mesh and optical link scheduling, I want to first build like an intuitive understanding of what exactly it is that we're talking about here. So really high level, we're talking about an internet backbone that you'd have terrestrially, but just in space, right? And there's some other problems that come with that, specifically on the dynamic topology. But the logical thinking here is that each satellite is just basically a router that can forward traffic through the terrestrial layer, right? So through a customer terminal, through gateway, an RF gateway, an optical ground station, or through any other satellite. And then I like to kind of explain optical meshes at a couple different layers, kind of working with a really high level and going down. So on the highest level, you have it from the access network viewpoint, right? So this is going to be your teams working on the actual customer terminals, on those hardware, and they essentially see it as a black box, right? So they would like to be able to forward data from a CT, and it's going to arrive at a customer at a RF gateway somewhere else around the world, right? They don't want to have to necessarily worry about anything specific. When then you get into your kind of what you might call like your networking group, your networking team, which is really the SDN control plane, they're going to see it as, a mesh or a grid of actual links. Now these links are going to basically have two high-level states, which is like it's working or it's not working, and they're going to have their own protocols, BFD, bidirectional fault detection for that. And then when you get down to where I am, which is like more like a hardware team on the data plane, we're going to really start to look at what are the specific metrics and components that we can make the actual free space optical links behave like as if we just had optical fibers in space that had perfect performance and high throughput. And this is just kind of like to summarize it, you got a space internet, and since we're talking about LEO meshes, most of it is going to be talking about this standard request response internet architecture. Later in the talk, we'll talk a bit about interplanetary networking, and that has a very different kind of model, especially when we're going past things like cislunar communication into deep space communication. As many of you know, your RTT is kind of too high, and just modern day, like right now, our use cases are different as well. So then going into some of the specifics of layers of communication, because I know not everybody is here is going to be super familiar with that. So why do we want to use lasers in the first place? It's because they can get much higher data rates than RF. And that's primarily due to the narrow beam width. We can capture more power or at a higher power density with a receiver. The con of having a narrow beam is that you have to use really tight pointing for the TX beam, right? Because it's so narrow, you can't just kind of point and send. So we have this whole technique that's going to be controlled by a subsystem on the spacecraft called pointing, acquisition, and tracking. And this ends up being very slow. You could think of it in the most basic sense. It's slow because at T2, between T1 and T2 in the diagram, we have to actually physically maneuver either the entire spacecraft or the optical terminal, which is going to be, on a 2-axis gimbal controlled by, DC motors or stepper motors, which might have slew rates of, 1 or 2, 5 degrees per second. If I have to turn my spacecraft all the way around 90 degrees, you can understand how it would take on the order of 30 seconds, a minute, or longer. And that's just for the coarse pointing. Then when we get into like T3, we're going to have link acquisition, which is usually defined by fine pointing. And this will be through a beam search process that can take even more time. And then just to put in perspective, this was a plot that we kind of created as part of a research paper that we recently did. And we basically simulated a bunch of different types of links in different constellations on different planets. And we computed kind of what we would expect different types of link durations to be. Not link durations, but PAT delay to be. And it's split between the coarse pointing, which is just the pointing delay, and then the fine pointing, which is the acquisition delay. And this is not super detailed, but I just want to give you guys an idea of what we're looking at. It's not on the order of milliseconds. That's not realistic. For deep space, it might be on the order of minutes to acquire a link, maybe longer. For LEO, it might be on the order of, anywhere from 10 to 30 seconds. And of course, that's going to change depending on your hardware specifications and some other things that we might be able to optimize that I'll discuss later in the talk. And this is specifically for the types of optical links we'll see in LEO mesh networks. Interplanetary networks we'll get into later. And so this is very important because it's going to give the intuitive understanding of how we're going to actually integrate other types of links into our schedule. So this figure on the left-hand side kind of shows the orange line, which are maybe your possible links or the links we've actually made. Keep in mind with our optical terminals, it's going to be a one-to-one mapping with the source and the destination, right? So we don't really have any MAC protocol that's going to be handling multiple access. We're really doing this PAT and acquiring a link between two terminals. What that means is that in this case, we have 5 optical links. That means we have to have 5 optical terminals on board. If, for example, we only had 3, we would be limited to 3 terminals at a time. If we then wanted to change links, right, so connect with a different spacecraft, we would have to do that PAT, pointing acquisition tracking process, to make the new link. Like we said, if that's going to be on the order of 30 seconds or 1 minute, it's not quite something that we can do in response to congestion control or on-demand load balancing. So there's some forethought that needs to go into basically how do we actually decide, which of these many links we do, and when do we do them, for how long do we do them, what are the data rates we can expect for them, and that's going to basically encompass our problem here of optical link scheduling. And just to describe a little bit more about these links, because I think the context is important. So your in-plane links, and these are called quite different things depending where you work or where you study at. In-plane, I'm referring to your forward and aft being in the direction of your orbital propagation. Cross-plane are going to be the planes on your left or right that are going in the same direction. Cross-sending is going to be that middle link that's actually going kind of right in front of you. So that, of course, you could think of it, it's going to have a very short contact window, and your relative velocity, also your Doppler shift, is going to be very high, which is going to make tracking very difficult. And then 2 new types that are kind of the most interesting, I would say, which would be intershell links. So generally, you're going to have your LEO mesh at 1 altitude, and then in order to increase density, we can actually have a single constellation with multiple altitudes. In order to prevent network segmentation between those shells, we might want to have intershell links, which you can think of it like the optical terminal. It's going to kind of point somewhere over the horizon, depending on, its maximum field of regard and what its motors can do to kind of make that link. And then one of the most interesting is space to ground. And this, of course, is going to be for optical ground stations, right? So kind of integrating our LEO optical mesh network terrestrially, but through optics instead of with RF, which is what it's traditionally used. And I think I touched on it a little bit, but I just want to make it very clear this difference between routing and scheduling, specifically in optical networks, due to the pointing and acquisition delay. So what it ends up being is that you have very distinct stages here, right? So you have this planning and scheduling stage where you create your initial contact plan based on what are your possible contacts that you could make. That's going to depend on your orbital propagator, field of regard models, and then you're going to actually select, well, which optical links are going to pair with which other optical links in the mesh. So this is going to effectively create your topology. That's going to then get sent out to the mesh through your SDN or whatever out-of-band method you're using. And then when it actually comes into the data plane in real time is when you're going to be doing the routing and forwarding. But that can only be computed, right? Your route tables are computed on the topology, right? So if your scheduling algorithm is bad and it creates a bad initial topology, your routes will also be bad, regardless of how good your routing algorithm is. And then this is just to kind of zoom in on that first section, which is what we define in our research as the optical contact plan design problem. And this is just a fancy way of saying like defining a mesh or defining a topology that also will include like interplanetary communication scenarios. And so, yeah, so when we want to actually then take these new links, like we said, maybe the cross-sending, intra-shell, or the space-to-ground links, how do we actually schedule those outside of the, our what we might call a standard optical mesh, which would be using, the in-plane and the cross-plane nearest neighbors. Those are then generally not going to change very often. So you could imagine your forward and aft, depending on your orbital propagation model, you might not really have to change it. For your cross-plane links, so on your left and right, you'll only have to basically swap optical terminals at the highest and lowest inclinations, because that's when your planes will cross. And unless you develop an optical terminal that has full 360-degree slew rate or field of regard, you'll have to swap. So when we want to move outside of those and bring in these new ones, how do we actually then embed these into the schedule, right? Specifically, I'm going to discuss mostly about the space-to-ground links, because those are quite unique in the sense that we're not going to have a very high density of optical ground stations due to atmospheric issues, which I think probably most of you guys are aware of, but if not, I can go just quickly into that. You're going to have atmospheric issues with your optical link. Optical links are way more susceptible to this than RF links. So we have to be very, very careful about where we place our optical ground stations, or else we'll never be able to get high data rates or maybe a link at all. Due to that, we're going to have very few optical ground stations. Generally, they're going to be placed, and there's a lot of studies on this that you can read up, but generally they're placed on the top of a mountain somewhere. And so it's not very common that you'll be able to just establish a link. So we need to be smart about how we actually integrate those in the schedule. And I'm just going to define this as kind of two separate layers. So how do we make the link? This is kind of more on the physical layer, right? So we might require a couple interesting technologies like digital beam combining, which is something that has been demonstrated by NASA for direct-to-Earth optical links, but has not really been done at a kind of LEO scale. And by that, I mean more like cheap. Instead of like billion-dollar projects, might be looking at $1 million project. Things like adaptive optics. They're very expensive, they're complex, and they're heavy. That's also why you generally won't have adaptive optics systems on board the spacecraft. They're going to be on the ground station. But one that I find really interesting is something like ARQ, or just basically buffering the data locally and waiting until you get an ACK. If you don't get an ACK, then you can retransmit it. Generally, your LEO mesh networks are not going to have onboard buffer, right? They're essentially, they get data in and they send it out one side. But the optical ground links make a really unique scenario for why that might be useful. And when we start talking about onboard buffering, then people start talking about things like DTN and bundle protocol. And I think it will be really interesting to then kind of implement that on the scheduling side. There's a couple high-level ideas here. One of the main ones is, well, just minimize the retargeting delay, right? If we could theoretically minimize it to let's just say 1 millisecond at a low bound, then we wouldn't care, right? We can just do whatever we want. We'll only, just physically be able to reduce it to a certain lower bound. And so we might want to start looking at things like this data aggregation buffering and store, carry, and forward. High level idea is that you can get data in towards your Leo mesh through whatever is your data provider, right? And that would be delay tolerant data, right? We don't necessarily need to get down. It's not a request coming through the internet. And what we can do is buffer a bunch of data, wait till we have a good optical ground link, and then send that all down. And that just provides kind of like a different business opportunity that you can leverage. And then now with the last couple minutes of the talk, I'm just going to go into the interplanetary side of it, because that's what my research focuses on a lot, and I find it's a quite interesting area. So in LEO networks, you might have some disruptions due to orbital dynamics, but you won't have things like maybe like planetary occlusions, and definitely not at the higher rate, and you definitely won't have delays, right? So when we're talking about interplanetary networks, we have these very, very long delays, and they can make things like on the physical layer of like acquiring an optical link very, very difficult. But it also adds an even more important note on how you schedule those links. So specifically with IPN networks, what we found was anything kind of past distance of the moon will require substantial rethinking of how we do the networking protocols, and that has a lot of the DTN stuff. And then when we try to bring in the laser comm, we don't have nice things anymore, like that stable mesh where we're trying to consider, well, what link should we swap to? Now we just have to figure out, well, what links do we select at all? So it requires basically constantly picking what links we want from a very minimal resource pool of DTE links and relay satellites. And we have to focus on things like sequencing, directionality, and contact window maximization. And with that, that's the end of my talk. I just want to thank everyone for listening.
Thank you very much. We got time for one question. You convinced or confused everybody? I think you were. I would be on the convincing side.
I hope so.
Okay. Thanks again, Jason.
Thanks, everyone.
This gets.
Was there a question?
No, I didn't see anybody in the queue. Okay, this gets us to our next talk. This is given by Renata Tejera. I have the clicker here for you.
Don't do it well still, so I need to have the mic. Is it okay if I go over there? Is it okay if I
stay roughly in here so that the camera catches you?
Okay. So I'd like to thank you again for the invitation. Just a show of hands, how many of you guys here heard my talk on Monday? Okay, lots of people, good, but there's still some people who are not there, so I'm not going to skip the recap. I have a very quick recap so everybody can be on the same page. But today I want to focus more on the experimentation and what we've learned about our adaptive bitrate and congestion control and how badly or well it works for Leo, as we will see. So this is not working?
Now it should work.
It should work?
Too many double clicks.
Okay, can I click now? Okay, it's working. Okay, so as a reminder, so this is part of the work from this paper here at Sigmetrics. It's actually the second half of the paper, which is the work of Liz Zhikevich, who's our professor at UCLA, Riz, who's here, who hopefully is going to help me answer all the congestion control questions you guys have, and T.Y. Huang, also at Netflix. So, of course, everybody loves streaming. We're from Netflix, and streaming is now the highest volume of traffic in the internet. And as this group is well aware, more and more people are relying on LEO now for internet connectivity. So Starlink has over 7 million subscribers. Jason was just telling us about Project Kuiper a little bit. So hopefully there will be more and more people connected using the LEO as a connectivity. So the question that we're asking yourselves is so how does LEO affect Netflix streaming. And mostly the data we have is for Starlink, so a lot of them we're going to be talking about Starlink.
Take the micro a bit,
A little away?
bit better.
Okay, so mostly we're going to be talking about, can everybody hear me? Yeah, okay, good. So mostly it's about Starlink, okay? So I'm just going to have my quick recap of some of the things we already discussed on Monday. So first, we showed what's the LEO's role in Netflix delivery. And we saw already on Monday that LEO keeps rapidly rising. And at Netflix now, we see that Starlink is the 19th ISP in terms of viewing hours out of like over 20,000 ISPs that people stream Netflix from. And it's rising particularly in Africa. We also looked into how good the connectivity is over LEO. And there, again, we see that quality is pretty good and comparable to terrestrial ISPs, in particular like visual quality, but we have this issue with increased rebuffers and bitrate switches. So we have good quality, but it's not super stable. And the focus of this talk today is, can we reduce these rebuffers and the bitrate switches? So that's most of the talk today, that's where I want to focus on. We'll see, like we're going to play with our congestion control and adaptive bitrate algorithms, and we'll see that you can tune it a little bit, it helps, but it doesn't fully get to the same level. Like you can't really close the gap with terrestrial ISPs. So let's dive into today's topic. So we have two levers at Netflix for playing, like adapting to LEO dynamics. One is the congestion control algorithm that will be adapting the sending rate to what we are measuring the network path. And the second is the adaptive bitrate algorithm, where we are picking which video version, which bitrate, which representation of the video that we're going to be requesting. So that will effectively reduce the amount of traffic that we're going to be getting in the path. So if you remember, for those who are not here on Monday, we saw that over Starlink, the throughput that we are measuring is actually lower than what we are seeing in other terrestrial ISPs. So one question we had is, what can we do with our congestion control to improve that? Can we reach higher throughput? So the first thing that Reese actually did was to look into the congestion window that we are seeing on Starlink. So here, what this plot is showing you is the relative maximum congestion window. So we are dividing the congestion window we are getting over Starlink by the congestion window we are seeing in other ISPs, okay? And the blue line is all other ISPs, and the green line is the top 10 most popular in terms of viewing hours at Netflix. And what we can see in this distribution very clearly, so we have the dotted line that marks the one, so that would be that the congestion window are equivalent. And what we see is that most of the time is towards the left, which means that congestion window is smaller in Starlink than in other ISPs. So if the congestion, we know that Starlink has higher RTTs, losses, and that leads to this smaller congestion window, which ended up with the lower throughput. That's the effect we saw last time. So the question was, okay, what can we do to increase the congestion window? So we tried something simple. So at Netflix, so we use the TCP New Reno, and then we said, okay, can we have it be less reactive to loss? And we use multi-CP for that. So the idea is, for every act byte, we increase the congestion window by 3 bytes, but then when we see a loss, we don't react as much. We just decrease it by 1 byte. And we A/B tested this on Starlink in over 1 million counts on Starlink. So 50% had our default New Reno, and then 50% we had this like less reactive congestion control. And here's my plot again, but comparing with this new version of TCP. And what you can see is that now most of the sessions we had are to the right of 1. So we were able to effectively increase the congestion window, which is exactly what we wanted. And what's the effect of that on throughput? So here I'm showing, so pay attention that the average throughput in the x-axis is in log scale. So the difference here are pretty significant. And our red line is what we had before for Starlink in terms of throughput. And you can see it's very far from the blue and green line, which is the other ISPs. But with this new, less reactive TCP version, what we get is the orange line. So we are able to effectively increase the throughput, okay, for Starlink using this algorithm, which is okay, we're happy. We got higher throughput, that's what we are trying to achieve. But it's not necessarily all free lunch. There are pros and cons of everything. So in terms of quality of experience, we had, so at the lower quantile of the quality, we saw that it improved. We had fewer rebuffers, we had fewer play delay, and bitrate switches, which is great. So for QoE, this was beneficial. The issue is that the network performance, there are lots of issues. So we have like over 300% retransmissions on average, and the tail latency in particular has increased a lot. Okay, so together they sort of made us reluctant to deploy something like this, and we keep experimenting. So what we learned from this experiment is that, you know, tweaking our existing congestion control helps, but it can't fully overcome this high reliability we have in LEO. We have this trade-off that we are getting more throughput, but also more queuing and more loss, which is not necessarily what we want. So I think that for us, as we are developing congestion control for this environment, we have to be expecting that bottlenecks are going to be moving because the paths are changing all the time, and we have these non-congestive losses. So together, it means that we need to rethink a little bit how we've been doing things. And people have seen that BBR in particular, and like the rate-based congestion control, is better for this kind of environment. And our more recent experimentation with pacing over Starlink also kind of shows that we get some good results with that. So we're going to keep experimenting on that front. And, you know, people have also been discussing, can we have our congestion control tuned, like we know Starlink does this 15-second reconfigurations and stuff. And so that's another idea that I think maybe is worth exploring, though I'm still a believer that if you can make algorithms that are more general, that you don't need to get any signals from the network itself, is probably ideal, but let's see like where we can go. So now let's look into what we can do for the adaptive bitrate algorithms. So for our ABR, we have we have lots of parameters that we can tune, but there are a few things that are more general that most of the ABRs have that we are playing with here. So one is the throughput discount. So if you're measuring the throughput of 10 megabits per second, and I have a discount of 50%, then the maximum bit rate that I can pick is 5 megabits per second, okay? So that's one parameter. The other is what we call the low buffer threshold. So if my buffer is running really low, I'm gonna be very conservative. Instead of picking 50% of discount, I might do 80% of discount. So I'm gonna sacrifice on quality, but I'm sure that I'm not gonna have a stall. I'm not gonna have a playback, a rebuffer. And the third one is throughput smoothing. So as we are getting throughput measurements, we need a way of kind of summarizing them. And here we're playing with an EWMA, and the half-life of the EWMA is what I'm gonna call the throughput smoothing here. And that means like how much of the history of throughput I'm taking into account in my estimate of throughput over time, okay? And we did a bunch of simulations and A/B tests to evaluate this. I'm gonna be showing you the simulation results because then we can kind of do the parameter sweep and we can see trends more clearly, but we validated these simulations with A/B tests as well. So here is the first parameter, the smoothing. You can see, so here I'm showing how we're increasing smoothing, and in the y-axis is the rebuffers per hours that we are measuring. So the blue line is Starlink, and the orange line is all other ISPs that we are simulating here. And as I increase the smoothing, as a decrease is moving, so I go toward that direction, you see that the rebuffer per hour is decreasing, which is what we want. It decreased for both the other ISPs and for Starlink. But you can kind of see that Starlink never reaches the level of the other ISPs in terms of rebuffers. So I can ignore, so by decreasing the smoothing, I'm considering just the most recent throughput values. So I'm acting really with the most recent information I have, but still it's not sufficient. We have a very similar thing for all the other parameters as you see. So for the low buffer threshold, as I increase it, I'm being more conservative, okay? So I want to have larger buffers. And of course, that means that the rebuffers are decreasing, but I have the same trend where Starlink never really reaches the level of the terrestrial ISPs. And finally, for the throughput discount, as I become more conservative and increase my discount, I reduce rebuffers, but I never reach the same level, okay? And of course, I'm not showing here, but if you go look at the paper, you can see as we change these parameters to reduce rebuffers, there's always this typical QoE trade-off, where if I'm reducing the discount, for instance, I'm going to be reducing my bit rate, so I'm reducing quality. So this trade-off between the quality, play delay, and rebuffers. So what we learned for the ABR, so we can help reduce rebuffers, but then there'll be increased bitrate switches, as you're saying, and some of the other QoE parameters. The issue here is the algorithm is really focusing on this average throughput, or sort of summarizing throughput of a single point estimate. And for Leo, we need to have something that's more variance aware, where we really can understand the variance a little bit more and avoid just switching on noise. So just to conclude, because I want us to have lots of times for discussion, Leo means very high variability, and we need the systems to expect that. So we haven't been building systems in this way. I mean, of course, we have congestion control and ABR to adapt to some variability in the path, but it's not the kind of variability that we're getting with Leo. And as a community, and as people here in this room, I think we should really be investing in more realistic testing, so open data sets and have simulators and test beds, so we can all work in an environment where we can test for these kinds of networks. And we should be thinking of Leo as a first class instead of as an afterthought like here, and really build for it. So I'd like to thank you all and remind you that I'm still counting on you, in particular people in Space RG, to keep looking up so we can build the promise of Leo and realize systems for that in the future. Okay, so please, questions?
Cool, thank you very much. So we have a bunch of people in the queue. James? Ah, there he is.
Okay. All right. Thank you very much for that presentation. I think this is really good. And yeah, I think we need the.
Yeah,
Okay,
I can't hear you
all
very
right.
well.
I was thinking you can see my name. Okay. My name is James Kunle Olorundare. I'm from Nigeria. And yeah, more about me. I'm the current president of Internet Society in Nigeria. So it's a pleasure to be here. And I'm happy to meet you too. All right, so back to the main issue. So I just have a couple of questions, or let me say comment to make on this presentation. Thank you very much. I think this is a very good one. And yeah, I think we'll need more insight in this regard, so to say. However, I just want you to clarify some things. Number one, on the issue of the quality of experience, I really want to know the model that you use for quality of experience. I remember that we started a conversation on this, on the modeling, and I'm aware that we have something like mean opinion score, but I'm not too sure if your model was actually based on mean opinion score. So I really want you to, expatiate more on that. I mean, the quality of experience side. For the quality of service, I don't have an issue with that, because definitely when you're talking about quality of service, you are talking about network parameters. So that's
so for
fine.
the, I can answer the initial question. So for the quality of experience, we have multiple metrics. So we don't have a single metric that will directly map to a mean opinion score. We use the VMAF, which is based on mean opinion score for the training. So but that's just for the video quality itself.
Yeah.
And then we look at the other metrics separately. As I showed here, like I just showed the rebuffers per hours today. Yes.
Oh, okay.
So we do have more people in the queue. Maybe I suggest that we keep this to one question per person at the moment. Otherwise, we will run out of time too quickly. Or if you have a second quick question, then ask it now. But just one more.
All right. Thank you very much. So the second question is on the issue of how we can actually look at the total bandwidth that is actually available for a particular country. I'm aware that, for regulatory purposes, we talk about geofencing, right? Geofencing, okay? That is to try as much as possible to ensure that wherever your satellite is beaming, it's contained within a particular environment where it is necessary. Excuse me. So can you actually, maybe for a particular country, tell me if you can calculate maybe the available bandwidth from Starlink? That's the question. Thank you very much.
So I don't know that our data will allow us to compute the bandwidth, because we just have the data from Netflix streaming. And so it's really biased in a way by our point of view. I cannot claim to be anywhere close to what Starlink is offering in a particular market.
Gori.
Gori Fairhurst, long-time satellite enthusiast. Can you go back one slide?
Oh, can you go back one
Which
slide?
Is it possible to the conclusion slide?
Which one?
Just to the
slide.
conclusion slide.
Give me a second.
Okay, so your conclusion slide says two things which I'm not sure I agree with. So I'm trying to
Great.
test you out. You say LEO means high variability. When you say LEO, you mean Starlink, or you mean every LEO system that might be proposed?
Thank you for asking this question. So I think that, as I discussed on Monday, there are some things that we are measuring that are clearly specific for Starlink, like they have this 15-second reconfigurations, these hard handovers. But the high variability, I believe, is going to be there for any LEO system, because of it's the nature of the system that you have to have handovers, you have to have reconfigurations. The links, they can't stay the same the whole time because the satellites are moving. And so that's where the variability is coming from.
Or maybe we can, I'm just trying to poke on two things, because I think as we go forward as a space research group, we can think about them. There are people working in various space agencies on multi-layered LEOs, where you can actually fall back to MEO constellations, etc. So maybe the high variability might change over time. And so I'm just worried that LEO means high variability is very true at the moment, and we should think ahead. So I love that you've touched on that. And the last one, I remember going back into my first days doing satellites, everybody said this for GEO. They said, protocols will never work over GEO, the internet will never work over GEO, yet that's not true now. So we have to think that when we design things for LEO, we're going to design things that will work over every type of LEO, MEO, GEO constellation, and not build one that's Starlink, one that's whatever, etc., etc. So let's think ahead to where we'll be, and be very careful to understand what links we're actually using, because I suspect your results are different if you do it in Africa versus you do it in North America versus you do it in Ukraine. So
yeah, so
this is tricky.
on Monday, I talked a little bit more about the geographical variability. Yeah. Here, when we are doing our A/B tests, it's a random sample. So I'm hoping our statisticians at Netflix are really good. They get us a very good allocation that covers well the customers we have. So that should be representative of what you'd see at large. Yeah.
And I wasn't meaning to be critical. Thanks ever so much for bringing this here, and let's do more of this.
Thank you.
Antonio Vicente, Cloudflare. Thank you for sharing this information with the community. I had a question related to the global reconfiguration combined with rebuffers. Do you see any correlation between the timing of the global reconfigurations and when rebuffers actually happen?
We don't have that information, unfortunately. Yeah, we just have like the overall rebuffer values, but it would be really interesting to see. Yeah.
Dirk Kutscher, thanks, Renata. Really insightful, and also great suggestions here on the last slide. So I just wanted to ask, what is the current state of simulation tools for these environments? I guess you must have used some simulation when trying out these things, right?
Yeah, so I mean, we have, for simulating what I did here, we have our own internal simulator, which uses our real ABR and stuff. We just use traces, like it's a trace-driven simulator. So we take throughput traces and play events. And so that's what I use here. Liz has done, like, in her paper, you can see that she did some analysis of the Hypatia simulator. She found some issues there, but I think that people are trying to address those issues and improve those simulators. And I think that having this publicly open simulators that are accurate are very important, because that's what everybody can use. Like we are using, like we have privileged traces, we have our own simulator, so it's a different beast.
So I'm thinking this could be a potentially very interesting activity for this group to develop or like nurture the development of simulation tools that are deployment independent, where we can do these different tests, maybe a bit like a hackathon activity, and then generate useful insights also for the more IETF activities in this field.
Yeah, I agree. I'm hoping
and get the insights from these from your observations and match them.
Yeah, I think that like for this working group, it would be research group. Sorry, it would be very nice to have try to identify benchmarks and tooling and test beds, because like if we're all working with the same basis, we can all test against the same baselines. It's really helpful as a community, so we can move forward together. Yeah, I agree.
Okay, thank you very much. This is exactly the discussion we wanna have, and also the insights to gain. We have 2 more people in the queue, but we are running 5 minutes late, and so Wes and Bechet, I'm afraid, but we have to grab Renata offline after the meeting. So sorry about that. We need to move on to our third talk. Thanks again, Renata.
You wish for Pablo as well.
Here comes you. So next talk is going to be given by Pablo. We have your slides up, and you have control. So please go ahead. Just speaking of simulation tools, now we come to testbed.
Okay, thank you very much. First of all, I would like to thank the chairs for the invitation. I appreciate it. And this talk will be about network simulators. In this project, it is a 2-year project. We are building this AI-enabled testbed for satellite mega constellations at Carleton University in Ottawa, Canada, under the supervision of Halim Yanikomeroglu. My name is Pablo Madoeri. I am a postdoctoral fellow at Carleton. Also, other partners are NRC, National Research Council, and the MDA company are DRD.
Oops, sorry.
Okay, in the agenda I prepared for today, I will be talking about 3 things. First, why the need for a testbed? Then, what type of testbed we are building? And finally, some demonstrations and the research we are doing with this testbed. As you know, we have moved from these satellite constellations, more classical constellations like Iridium and Global Star, with tens of satellites, and now we are talking about these satellite mega constellations with hundreds or thousands of satellites like Starlink, but also some others like Kuiper and the upcoming constellation here in Canada, Telesat Lightspeed, from which much of our research is inspired by. Also, we can move from this only RF links to include optical links, as in the talk from Jason. There are many challenges there, tracking, acquisition, and so on, scheduling, contact plan design. In addition to that, we can move from more simple architectures in terms of networking, like bent pipe, where the packet goes up to the satellite. Very little processing is done there, and it is sent back to the ground. And now we have this mesh in the sky that are able and more capable of processing capabilities. So we can use those processing capabilities, but that requires orchestration in order to take advantage of the benefits. So in summary, we need these more advanced techniques. We need also to be able to, first of all, develop those techniques, the proposals, and then to validate those. So that's why we are building this testbed. In the architecture, we are simulating. We have, of course, the satellites with the optical inter-satellite links, but we also have these optical links in the feeder link. That is the link between the satellite and these optical ground stations. There are many challenges there in terms of weather conditions, like cloud cover, which doesn't affect so much the RF links. In addition to that, we have, of course, user terminals connected as usual with radio frequency links, or other users like an aircraft that could be using an optical link also with satellites in the future. We are putting the focus on transport and network layers and making some abstractions of the link and physical layer. We have 3 pillars in our testbed. A first part about simulating the orbital dynamics. It could be MATLAB or STK. Here is where we configure a scenario and compute this topology, which is evolving over time. Then we complement that with some tools made in Omnet. Omnet is a framework that allows us to model this network protocol dynamics at the level of a packet. And here we can configure link capacities, node capacities in terms of buffer, traffic demands, weather conditions, routing, and transport protocols. And finally, of course, we want to train some machine learning models that then we can incorporate back into the simulator and see how they perform. In this testbed, so we have satellites, we have the user terminals, these landing stations or ground stations, and also the SDN controllers and SDN switch. Of course, we didn't start from scratch. I have to mention that although this tool is not open source, it is using a lot of open source code, so many of us could reuse these tools to implement an open source simulator for the community, right? So there are the links, the INET framework that allows us to simulate internet protocols, OR3 that has all the part of orbital propagation, Atlas also, which incorporates INET protocols, OpenFlow extensions. To simulate traffic, we have the H3 library that allows us to map each part on the ground to these hexagonal cells, which are used by Uber and many other simulators. And also we can simulate traffic demands by mapping population density to these cells. So population density, time of the day, because, for example, Canada has many time zones. When there is a peak hours in one cell on the East Coast, it could be the opposite on the West Coast. So considering this aspect, I think is useful when modeling the performance of these routing and transport protocols. Okay, I had a few videos, but I had to put this more in snapshots for this presentation. This is Omnet. It allows us to configure some parameters about the orbits, the constellations, also about the traffic over here. This is how it looks. We have this mesh on the sky with optical intersatellite links. We have a ground station here in Montreal, a user in Nubik, which is sending a ping packet by using this mesh toward the ground station. Omnet gives us many capabilities to have an intuitive understanding of what is happening in the network, right? What are the different interactions? For example, we can zoom in inside one of these satellites or ground stations and see all the functionalities performed by different layers at the application, transport layer, network layer, and physical layer, and how a packet traverses those submodules to reach the final destination. Also, in terms of traffic, we have the capability to model different distributions, constant bit rate, normal, exponential distribution, traffic burst, which is maybe closer to these more realistic traffic distributions. We can model the size of these peaks and also the sleep times or the gaps over here. And here, well, you have a view of also how it looks with different population densities close to Toronto, and maybe the green cells with less population. This is to show a bit of the accuracy at which level we are modeling things. We can use Wireshark to capture traffic at each of these interfaces. So these packets have all the fields that a real packet would have on the internet. And this is our objective, is to integrate simulation environment with an emulated environment, because we would like to know how, let's say, an onboard computer would perform, but we need the scalability that can be done by using a simulator, right? So we have here the simulated network. When a packet arrives to a simulated node, we want to connect it to some real hardware or a process in the operating systems to make the decision over there, feedback that decision in the simulator, and continue the whole process in the simulator. OMNet gives us good capabilities to do this. We have many lines of research. I will tell a bit about each of those very quickly. The first one is, once we have connectivity, we are interested in quality of service, as Renata was mentioning in the previous talk. So here in this demonstration, we have some toy example over here. We have some user terminals here in the north, and we have some ground stations, let's say, connected to points of presence on the ground. The objective is to send from these user terminals to the ground stations, right? And if we don't apply any policy for handling the quality of service, the traffic generated by this user terminal and this user terminal, we will share these links over here, right? So if we have different qualities of service, as it is mentioned in these standards, differentiated service architecture, we have different traffic, expedited forwarding, assured forwarding, and best effort traffic. If we have different traffics by these users, and there are no special policies, all traffics will be competing here in the same links, right? The first thing we can do is to consider a queuing architecture at this satellite, for example, so that traffic can be inspecting these differentiated services, sent to particular queues, and in that way provide more quality to the traffic which is demanding that. The second step would be to jointly optimize the queuing and the routing, right? Because in the previous, we were doing only queuing. But here, for example, if it is not enough, what we can do with queuing scheduling, we can also change the routing decisions, and this traffic could be sent through this different route. We have some curves here, maybe not much time to explain, but we demonstrate that by combining routing and queuing optimization, we can provide better performance to the traffic that requires. We have also done some research about software-defined networks. In particular, we are assuming that these controllers could be activated and deactivated dynamically over time, like as if they were Docker containers, right? That would be in order to save energy. Of course, there are some penalties and complexities for having more controllers. But if we have more controllers, we can reduce the latency to establish this route. So there is a trade-off, an interesting trade-off there to investigate. And once these controllers are deployed, like how we associate from satellites to controllers, from which satellite to which controller. Another line of research is about the feeder links. As I mentioned, we have here the effects of cloud cover. So there are interesting dynamics also here, because if we use radio frequency-based ground stations, maybe we have more reliability, right? It doesn't get so much affected by weather, but data rates are lower. And here, maybe we have optical ground stations, much higher data rates, right? But much more propense to these adverse conditions. So how we handle this site diversity on the grounds, how we do scheduling, and how we take advantage of weather forecast, right, in the next hours in terms of cloud cover, in order to plan which optical links we are going to use with the ground. That is also another interesting topic. And to finalize, we have this other line of research, green traffic engineering for satellite networks using segment routing flexible algorithm. Here, the idea is to activate or deactivate these optical links in the sky in order to save energy, but at the same time, we don't want to compromise the reliability. Thank you.
Thank you very much. So we've got time for one question. I think John Ping is in the queue.
Yeah, I just have a quick question. Like, this is a very great tool, but when people can use it outside of the university, can you hear me?
Yes,
Yeah.
we can hear you perfectly.
Yeah,
Okay.
can you repeat, please?
Yeah, I think this is a very good tool, like enough other people can use. So when you're going to like put it available publicly for other people to use as well.
Yes, as we did this with the contract with MDA, we are not allowed to share the code right now. But as I mentioned in one of the slides, all of this is based on open source code. So I think that could be replicated, and it could be also like a target from the group. I would be happy to provide some other like help and support to make an open source tool. But of course, if there are some talks with Carlton people, there can be some collaborations and some special agreements over there. So yeah, there are a few possibilities.
Okay, thanks.
Okay, yeah, thanks again. Ping, you should have control for the slides now. This gets us to the next talk about measuring LEO satellite networks, what we have learned about routing, and go ahead.
Okay, thank you. Sorry, I cannot make in person, so I have to present online. So I think everyone knows like what a LEO satellite is. So in this talk, I'm going to focus on a few aspects of it, including like addressing, naming, and routing. So in terms like addressing, and there's not much difference from like Starlink and other, let's say, service providers. By now, like Starlink claims yesterday after I sent out the slides, they claim they have like 8 million users now. So I should up that beforehand. And you can see, let's say, I don't think you can see my pointers like on the slides, but on the upper corner, you can see if you subscribe to Starlink, you get the router and antenna you install like outdoor. And from there, like there's a specific addressing schemes, for example, like list on the left side of the column. And from there, there's a big, let's say, antenna go through the satellite and also ground station toward the POP. So this is like one of the bigger pipe we can measure, and we can see a lot of interesting about it as well. For OneWeb, it's different because OneWeb targeting mostly like enterprise and business users. So that's why most of the OneWeb users, they bring their own IP address spaces. So that's from the user side. And for Starlink infrastructures, they have their own, let's say, IP addressing schemes, which is quite interesting. You can see in the next few slides. In terms of naming, that's also interesting. For example, for Starlink, it's names like the dish with a specific name, and it's also named like users, customers in a very specific way to be like a POP specific. So from the, let's say, user name, you can host a name essentially, like we can find out, okay, which POP this user is associated with right now. And for OneWeb, again, like it's custom, let's say, bring their IP address, also bring their like a name as well. And for the Starlink backbone, Some part of the backbone, they don't have any like name associated with that. So that's why I can make the things more interesting to find out. So we can see like later. Of course, routing is the most important thing, like for any computer network. For Starlink, at the access side, so for example, like kind of the user terminal, the dish, is going to talk to satellite. And the Starlink dictate which satellite are talking to. So the user has like no choice. But this choice depends on the location of the kind of user and also the dish orientation as well. So many people have already observed, so there's a regular handovers every 15 seconds for Starlink. But in addition to that, there's also something called a faster switching enabled by Starlink. If the satellite is obstructed, the Starlink has the capability to switch to a new satellite within that 15-second interval as well. And once you reach the satellite, it may go one or multiple satellites until it can reach a landing ground station. So from there, they have to go to the POP to go to the internet. They cannot go to the like kind of internet right away. So this is how the like kind of inter-satellite link look like according to the people at let's say kind of Starlink for a dish in Antarctica to a landing ground station in Chile. And this is how the let's say kind of Starlink performance look like for people like kind of in Antarctica. You can see something right away. The minimal round trip time from the user dish to the POP change regularly every 15 seconds. And there's a handover, let's say kind of delay spike and a packet loss as well. Not only they have 15 seconds, this 15 seconds is also globally synchronized. So you can see for different let's say kind of dishes in the same region, you see highly correlated handover behaviors. And also like in the up right corner, you see the like distribution of the latency. It's still the grouping effect as well. So could it be, let's say, kind of associated with the same research station there. But that's not all the story, because like kind of after you reach the satellite and come down, you have to route your packet on the ground. So this is something actually is more interesting because like again, Starlink is not like a totally satellite. It has a global infrastructure as well. So this is like how the Starlink backbone look like in 2023. After our exploration, we can find out like kind of it's in different regions. It's follow a typical, let's say, kind of global ISP architecture. And we have new things added in 2024 and 2025, like the red color indicated like kind of the new links and the new POPs in North America. And the blue one is the latest one. For example, like Kansas City is the newest POP in North America. And once we know the POP location, we can roughly estimate the port boundary as well by using the Vora diagram. It's pretty close, actually, very surprisingly. Expect like some POPs, for example, like Chicago versus like Minneapolis, because Minneapolis, there's not much content there. The Minneapolis is a little bit less than estimated through our drive test. And this like the backbone in South America, in Europe, Africa, and Asia Pacific, the same like notation. Like the black one is the 2003 backbone, the red one is the new edition in 2024, and then like 2025 is in blue. And this just gives you the big picture for the entire world for Starlink ground backbone. Very quickly, we found something interesting about Starlink, something called a suboptimal routing, because Starlink right now is something called home pop centric. So whenever like kind of your packet lands on the ground, they cannot go to the internet right away. They have to go to your home pop. So in this example, like we have one dish in the west coast of Indian Ocean. They want to reach another dish, let's say kind of on the east coast of Indian Ocean. So the shortest path would be like just go over the like Indian Ocean in interstellar link. But in 2023, Starlink actually kind of go all the way around the world from like Lagos to London to like New York to Denver to Los Angeles, Sydney, and Perth. So the round trip time is more than 600 milliseconds. It's almost like a geo. But like kind of in 2024, because they have a new POP in Singapore, so they can cut this like latency to about 300 milliseconds. But ideally, if you go over the like ocean directly with interstellar link, this can go as low as like 100 milliseconds instead. But this is not only the issue with routing. We also have the routing between, let's say, kind of the network layer and the, let's say, kind of content or the application layer. So there's a mismatch between the kind of POP and the content. For example, like until last year, there's only like one POP in Africa. And before that, all the African users, they have to use POP in Europe. So in this case, like enough, it's long time for them to reach the POP, but the content is nearby. And then later, they will associate it with like a POPs in Africa, but sometimes like the content is not there. So they have to still go, let's say, to Europe and maybe to other places to get content. So that's why there's a trade-off between like enough content latency versus like the POP latency as well. This roughly the same thing, but I give you like more details. For example, this particular user in Zambia, and he was associated with like a Nairobi POP. If they want to reach Cloudflare, sometimes they reach like the Cloudflare like in Nairobi, but sometimes like they will load balanced to Johannesburg. So in this case, like if you get a 100 millisecond addition due to like go to a new POP as well. But the interesting thing here is like the latency is interleaved. It's not like consistent in terms of the balancing. Again, like routing is a central function in any networks. So I believe there's a lot of things like this research group will be interested in looking into as well. So I'm not going to like repeat them right now. So last but not least, we're also putting together a cross-country test bed in Canada, and we're also federating with like other test bed around the world as well. So our goal is to have at least one, let's say, low Earth orbit satellite test bed node in each of the province and the territory in Canada. So right now we have about like 14, because some like territories like they are much bigger. We have multiple like nodes there. So this is my like last slide. So you can find my contact information, but more importantly, if you're interested in our research work, you can find the link at the oak.uvic.ca LeoNet. It has all our research work, papers, data sets, and the code. We make all our data available to everyone. So not only ourselves, all the research communities can like use the code, use the data to conduct their own research as well. And we're also putting together this like a cross-country like test bed. And most recently, we were lucky to be selected by the DRDC in Canada to together with another team of researchers at the UVic to build and launch a satellite by like in November 2027. So that's on my presentation, and welcome the questions.
Thank you very much. So we have one question in the queue. One person. Yes, no.
Maybe the question was Q was for the last presentation.
I don't know.
Yeah, James. Oh, he's there.
He's on his way.
Okay.
Yeah, actually, I think he's right. It was supposed to be for the last presentation.
Okay. Then good.
Yeah, so I don't know if I can still ask the question or
For the previous one.
Yeah, exactly. For the previous one, not for
I think you can. It's easier to take
right.
that offline. Okay, thanks. Jonathan. Got some time.
I see that you're asking people to contribute to the data set by putting probes in their network and everything. Wouldn't it be just easier to ask the Starlink providers and everything to provide you with metrics and stuff like that for your city?
Yeah, ideally that's the case, but unfortunately, you probably know it's very hard to deal with Starlink. And we are probably the only like research group intact with all these 4 leading research companies in person, like Starlink, OneWeb, Kuiper, and Telesat, like Lightspeed. But again, it's very difficult to get any data from them. So our approach is we're going to collect data. We're going to provide that data to them to let them know how their work network look like.
Okay, so it's more like be a good LEO operator citizen and share your data type of thing. Just like we do with the internet, be a nice internet guy.
Yes. It might be the vision in the next few years, but right now the situation is pretty different in the sense each company they can tie their own stuff very closely. But as researchers, we have advantage because we can provide let's say a level playground for these companies to say we have this test bed across country. Bring your nodes here. We can do a fair comparison for everyone as well.
Okay, thank you.
Thanks.
Okay. No more questions in the queue. That allows us to catch up a bit. Thanks again, Jumping.
Okay. Yeah, you're welcome. Thank you.
And this gets us to our last presentation of the day. also being given remotely.
Yes, good morning. Is my audio okay?
Yes, sounds good. You should have slide control. Let me reset the timer for you.
Yeah, I think I do have slide control. Yes.
Okay, floor is yours.
Okay, thank you. So hi, I'm Maxime Pirot. I'm a networking engineer at Aerospace Lab, where together with 300 colleagues, we're building and designing satellites from the payload to the platform for various types of missions, but also with an interest for internet access satellite constellation. So I've submitted this this draft that I'm going to present a bit of the context, not get too deep into the document, but just give you an outline of what it is about, and then this will lead the discussion of where to take this. So there's been a bunch of introduction on satellite constellation already, and the main message of this introduction here is that as time advances, they get more complex with more shells. And the big change also is that we went from a band pipe topology in earlier deployments, so the OneWeb constellation and the V1 satellites of Starlink, they weren't equipped with any inter-satellite link technology, and now we have optical inter-satellite links, coming in. And so with this, the satellite constellation becomes a network in itself. And as Jason introduced in the first talk of the session, then there's the question of a control plane to provide these services to the client. So when I started looking at this, I was looking at those constellations and trying to figure out what network topology do they form in the graph sense of things. And so essentially, I was trying to capture, trying to understand what I need as parameters for a given constellation to try and map what we could see in orbiting the Earth, let's say, and map this to something that is more akin to the world of the network researcher or network community. So having some form of topologies where satellites are connected together to form a mesh network with different links, and have this represented, or at least derive this so we could study the actual network that is formed. So I have on the left side a fictional constellation with some parameters I defined. And so as I was looking into this, I proposed a code to represent the different parameters of a constellation. So I've here listed a summary of those parameters. So it's currently it's considering altitude, inclination of the orbits, number of total satellites, number of orbits, and the phasing between the orbits. And with these parameters and a given pattern, so there is two patterns. I don't have the time to explain them in details, but the draft do contain a bit of text trying to explain them. So together with a given variance, so local star or local delta, we can fully capture the constellation. So in the draft, you'll find the ABNF definition of the code. So as you can see, constellation is composed of a set of shells. Each shell has a Walker type, so D for delta, S for a star, and then has all those parameters we were discussing, altitude, inclination, and parameters of the plane, so number of total satellite and all this. The reason for the separators of the code and the general aspect of the code is historical, because I based my work on the format of Tim Vanderlee that was open source on GitHub. But this could be changed, of course. So example of use of this code. So together with some description of existing constellation that I could find online, then we can see on the last column how this transposed into the code. So the interest of the code is that it is now non-ambiguous and machine parsable. And so other use of the code, obviously, is building some tools, doing some computations. So here I have still on the left side my fictional constellation with its code. And then in this case, with a bit of math, some Python libraries, I could compute the distances between two satellites of neighboring orbits. So satellites with at the same rank, but on neighboring orbits, that are outlined in white rectangles on the left. And so you could see on the right-hand side a graph that has on the x-axis the time within the orbital period, and then on the y-axis the distance between those two. And you can see that they follow kind of a two cycles of a sine form. And so they get closer as the orbits are getting closer, obviously. And so the orbits are crossing twice throughout the orbital period, and then they get further away. So this is obviously just a simple example. There could be many, many things we could build on this. But the current document is limited in a sense. It's an initial version and has a lot still to be built there. So for instance, the link configuration is implicit. For local delta, I assume 4 fixed links, which is kind of the traditional way of looking at things. So 2 would be in plane, and then 2 would be cross plane, which is fine for small to medium constellations. But then, as researcher pointed out, for mega constellations, there's much more that could be done. So there is this paper dating from a few years back at CONEX, where they looked at how the satellites could be connected with some patterns that are repeated within the constellation. And all this is only looking at the aspects of the network graph, which was already enough for me to try and do some experiments with routing protocols, for instance. But then there is obviously an entire other avenue, which is about link and the quality of links. So their priority, their constraint. And then also, like we were discussing on the list, maybe there is some kind of a space RG toolbox to be made. So we were talking earlier on in the session with simulator. Maybe there's something in between the full-fledged simulator and then kind of a toolbox that gets everyone up to speed. And then obviously I've touched upon it, but the link topic is much more broader than this, than these things. And it sparked some interest in the group for optical intersatellite links, and also for radio frequency intersatellite links. Would be interesting to see whether we can module how they behave and capture this as well. So that's it. Thank you already to the group for the comments on the list. I opened the GitHub if you want to propose your IDEs as issues or pull requests. And then I would also invite you to try and use the code in your tools, because that's one way to give feedback also, is to try to use it and see what how it works for you and how it doesn't work. And then, yeah, I want to also thank Tim van der Lee for his open source contribution that this work is based on. So yeah, that's it.
Cool. Thank you very much. So on your question, one of the bits that we certainly would want to do, so this could be a great example of a format tool description and something that could be contributing to a common toolbox, as you call it, and as we would envision that, to find common ways of describing all things from constellation to experiments and so on. So absolutely. Yeah, but thanks again. So don't see any question. This gives us 2 wrap-up minutes. So today we have seen a bunch of quite different talks on laser link stability, on simulator, on real-world observations, then on measurement campaigns and data sets, and now on other contributions. So this is exactly the kind of diversity that we are kind of hoping for. Maybe one open question to people in the room and online. We want to be meeting again next IETF. Are there specific suggestions on things that we ought to be doing as well come to mind? One, you can, first of all, of course, please do subscribe to the Space RG mailing list and share your thoughts there. But if you have any ideas that we should be taking into account now and that we should have as a takeaway, take-home message for now, then please speak up now. I have Dave in the queue.
So there's a bunch of recent stuff in the press about the possibility of getting a lot more computation in orbit.
Mm-hmm.
And since we're trying to be sort of a forward-looking research group to do research that potentially can maybe stay ahead of the commercial guys deploying stuff and help, I think calling out to see whether we can bring in people who are trying to figure out what the characteristics of LEO or MEO, at least in orbit computation elements, and what the characteristics of how the characteristics of the traffic might be really different, and other trade-offs might be different, would be really great to bring in here.
Yep, that's definitely a good idea. Other comment? Thanks, Dave. Let me remove. Okay, out of the queue. James.
All right. Yeah. Thank you. Oops. Electrostatics. Thank you very much. So, yeah, I think this may be an opportunity to bring up the issue I actually wanted to ask question on, and peradventure, it could be something that can be looked into as per what you asked for. So, I think it will be a good idea if this working group can start looking at how to calculate traffic demand, which I think is related to what the penultimate speaker spoke about. I think that may be a very good idea, looking at, okay, the aggregated demand from each, maybe let's say, country. I think that may be a very good one, bearing in mind that you may need to set geofencing so that at least you will be able to concentrate on a particular country. I think that may be a very good one. Then, looking at it from the other way, it should also be a good idea to start looking at, okay, fine. We're looking at traffic demand from a particular climb, geospace, and so on and so forth. Let us also try to calculate the available bandwidth from a particular service provider. In this case, peradventure, we can just focus on the LEO service provider, since that is more like something that is trending, and it seems interesting to each and every one of us. So let us get what bandwidth is available to each country, and I think that's going to be an interesting study if you ask me. Yeah.
There was a great talk at, I think it was at IETF Open, on capacity available across different countries, which is an example to that. And so this is the idea of what you can actually do to serve certain user groups in certain regions on the planet is also something that we would want to keep in mind. Thank you very much. Okay, our time is up. Thanks very much for everybody attending. We'll see you at the next opportunity.
Thank you.
Thank you.
Very nice. Yep, good job. Thank you for leading this. Yeah.
Next time you were up.
Yeah, happy.
When we have this 30 of what was presented. They are all up already on the materials page.
Yeah, you can get it
already, so we can access to all of them.
Yeah, sure.
Yeah, this was very good. This was a lot of fun.
Should we close the room now somehow?
Actually, let me leave the room here.
Yeah, zobaczmy,